This is the second in the series graphical representation of motion in a straight line. In the previous examples, all data points lay on the same straight line, but when we plot experimental points, this is rarely the case, so we get something like what is seen in the graph below. When the data points are scattered, we draw a line of best fit through the points. We want to calculate the gradient of the line in order to determine the velocity. So we draw a line of best fit first, and we use the line for our calculations, not the plotted points. The intention of the line of best fit is to smooth out the errors in the plotted points, and we use as large a sample as possible so to increase the accuracy. How do we draw a line of best fit? On a graph we do this by eye, and we draw it through the points so that either there's an equal number of points that lie on either side of the line, or the sum of the distances of the points above the line are roughly equal to the sum of the distances below the line. Using the straight line of best fit, the gradient is given by the rise over the run, and in this example, the rise is equal to 21.3 less 1.5, reading off the graph, and the run is 6, because we're looking at the interval from 0 to 6 seconds. And then calculating that, we get 19.8 divided by 6, which is approximately 3.3. So we can say that the velocity is 3.3 meters per second. In this example, we can see that the line of best fit is not always a straight line. If we look at the table first, at time 0 the displacement is 2, after 1 second it's 3, and then goes on to 6, 11, 18, 27 and 38. The displacement increases each second, which means the object must continue travelling in the same direction away from the origin. It's moving to the right because it's positive. To look more closely at the example, we do what we did earlier, which was to put a point along the displacement axis at each point in time to show where the displacement was. And we can see that at each second the object travels further and further. Between 1 and 2 seconds, the object travels from a displacement of 3 meters to 6 meters. So in that interval, the object changes its displacement by 3 meters. But between the second and third seconds, it travels from 6 meters to 11 meters. So in this interval, the object changes its displacement by 5 meters. So it's increasing its displacement each second by greater and greater amounts. Clearly, the object is speeding up. It's traveling greater distance from 1 second to the next. So we say that the velocity of the object is increasing, or the object is being accelerated. Here's a summary of our rules so far. The displacement time graph for a constant velocity motion is a straight line, and the gradient of that straight line is equal to the velocity. The displacement time graph for a changing velocity motion is curved. The gradient is constantly changing, and the changing gradient indicates the changing velocity. And thirdly, the gradient of a curved graph at a particular point is the gradient of the tangent to the curve at that point. The gradient is the instantaneous velocity. Continuing with the previous example, the instantaneous velocity at 4 seconds is equal to the gradient of the tangent to the graph at 4 seconds, or the rise over the run. Here's a new example. First have a look at the table and see what's happening to the displacement over time. At time 0 the displacement is 0. After 1 second the displacement is 9, after 2 seconds it's 16, and then 21, 24 and 25. We can say that the object is moving, and we can say the displacement increases each second, so the object must continue to travel in the same direction away from the origin to the right. Now looking more closely, between 1 second and 2 seconds, the object travels from a displacement of 9 meters to 16 meters, so it changes its displacement by 7 meters during that second. Then, between 2 seconds and 3 seconds, it travels from a displacement of 16 meters to 21 meters, so the change in displacement there is 5 meters. What's happening? We can say that the object increases its displacement each second, but it's increasing it by smaller amounts from 1 second to the next. What does this mean? It means that the object is slowing down, or the velocity of the object is decreasing. We still say the object is being accelerated, but some call this type of acceleration a deceleration. The same rules as before still apply, namely, in motions represented by a curved displacement time graph, the velocity is changing, and the instantaneous velocity is equal to the gradient of the tangent to the curve. But where velocity is decreasing, the gradient decreases with time. And that's the end of this second session.